let us take one specific problem instance which was sort of used as the sort of motivating example right from the beginning for this whole problem of scheduling, right. So, it is a very common example that you are likely to come across if you are reading any literature in this area. So, I am going to use the same example because it is a nice task graph that allows us to sort of visualize a lot of these things quite easily, right. And the problem is essentially that you want to do numerical integration of a particular differential equation, right. The equation that is given is y double prime plus 3x y prime plus 3y equal to 0. Yeah. 0. And what I want to do is to numerically solve this or numerical integration of this in the range x from 0 to some a. Okay. So, the way that I would normally do this is I start off with some initial conditions for y, but apart from that I start off with x equal to 0, and then I can essentially put together something called the forward Euler equation, which all that it's doing is essentially saying that at the next time instant, right, some delta that I am considering, next there is no time over here, but the next value of x essentially corresponds to x plus dx. For that, what should be the value of dy that I get, and how should y change with time. Okay. So, in order to solve this, one way of sort of rewriting this expression is to bring in a new variable which I will call u is equal to y prime, the first derivative, right. So, these derivatives are obviously with respect to x, so it's y prime is basically dy by dx over here. Okay. So, then what I can write in this case is u prime is equal to y double prime is equal to, I take the remaining terms to the other side, what I get is minus 3x u minus 3y. Right. So, I have just taken that top equation y double prime plus blah blah and pushed the two terms to the right hand side. Okay. So, what does this mean? It means that the new value of u is going to be given by the old value plus u prime dx. Okay. X new is going to be given by x old plus dx, u new is going to be given by u old plus u prime dx, and y new is going to be given by y old plus, well, y prime is u, so u dx. Okay. So, it does not really matter, you do not need to worry about the math over here. What we are trying to show is that you can start off with something as simple as a differential equation and construct a task graph for that, which then needs to be scheduled. Okay. So, if I go ahead with this, then essentially what this corresponds to is this, the computations that I need to perform are x to x plus dx gets the value x plus dx, u gets the value u minus 3xu minus 3y, or just expanding this out, what I will end up with is minus 3xu dx minus 3y dx, and y gets the value y plus u dx. Okay. So, this essentially corresponds to the set of 3 equations that I need to solve. Okay. So, I am going to draw a data flow graph corresponding to this, okay, and use that as my starting point. So, what I have is, this gives me the new value y plus u dx, this gives me the new value of y, and the last one is 3xu dx minus 3y dx, etc., etc. Okay. So, this is the task graph that you can construct for this particular set of equations that we have over here. Now, if you look carefully at the task graph, you would realize that this is probably nowhere near optimal, right, because for example, this term over here u dx gets computed twice, right. There are two different places where the same u into dx is being done. I could also probably have done some 3 into dx at one shot and therefore used it in order to separate out, to avoid doing the computation twice. Those are what are called optimizations, compiler optimizations, right. A normal compiler would normally be able to pick up the fact that you have something called common sub expressions in these computations and therefore do some optimization. Our goal is not to do that. We do not care about whether this task graph is optimal or whether it is a good task graph. All that matters is we were able to start off with a problem, convert it into a set of equations, and from those equations convert it into a task graph with dependencies. Okay. So, that is all that we really care about at this point. So, do not worry about the optimality or otherwise of this task graph. All that matters is the fact that there are a set of tasks with dependencies that we can then analyze in this way. This, by the way, is giving us the value u nu, right. There is one further computation that needs to be done, which is that the x plus dx, the x nu, I need to essentially compare it against the value a to decide when that graph or the computation needs to terminate. Okay. So, if you look at it, the total set of computations that I have are this. There are 11 computations out here, 6 of them are multiplications, the other 5 are either addition, subtraction or comparison, right. So, rather than saying I need separate hardware units for all of those, addition and subtraction at least we know are pretty much can be done by the same hardware, right, because after all you just use 2's complement and addition and subtraction essentially become the same thing, right. Comparison is also essentially the same thing, because all that it involves is you do a subtraction and check whether the result was negative or positive. Okay. So, what we have is 5 operations that I am going to call ALU operations. Okay. So, a total of 11 tasks that need to be scheduled, and what we are going to look at is how do I go about systematically, and are there any ways by which I can systematically solve this particular problem.